power editing won't save me here. Okay guys, welcome to Sunday Afternoon Physics with Nelso. We're going to kick off electric fields today, starting with Coulomb's law, how it relates to proportionality. Again, pretty much everything does. Also how it relates to Newton's third law and how we can get around adding these forces together using vector addition. So first of all, we're going to kick off with Coulomb's law. Coulomb's law is this behemoth. Okay, so it's a force, we're going to stick that on there. I'll talk about that a little bit more in a minute. What we've got is this hideous looking thing here, 1 on 4 pi epsilon naught. If you have a look on the equation sheet, you'll actually see that it's just a number. In this case here, it's 9 times 10 to the 9. Q1 and Q2 are the charges, R square is obviously the distance between those two charges. We don't look at the 4 pi epsilon naught as a thing, we look at 1 over 4 pi epsilon naught as the constant. It's a really weird way to write these things. It's a little bit messy, a little bit horrible. It used to be the letter K, but then textbooks, American metric system, whatever, imperial system, just became easy to do this. K is also kinetic energy, remember. What we're going to look at is how this relates to proportionality. So in the last topic, we looked at gravitation, and we had Newton's law of universal gravitation, where we had a force was equal to G m1 m2 on r squared. All right, so G in that case was the constant. Here, this thing is a constant. All right, masses are the things that are attracted to each other because of gravitational fields. Charges are the things that interact with electric fields. So we have this, the mass was the physical constant or the physical characteristic in Newton's gravitational force. In Coulomb's law, the green one here, Q, the charge, size of the charge. So if you obviously have more mass in a gravitational field, you have more gravitational force. If we have more charge in an electric field, we obviously also have more force. So if we were to get one of these charges and we were to double it, so let's say we've got this thing here. So what we're doing is doubling the size of Q1. We've still got Q2, we've still got R squared, we've still got the hideous constant, and now we've got this new force, the pink one. If we were to take that factor of 2 out, which we quite clearly can, we've just got a number that's multiplied by another number that's multiplied by another number that's divided by the square of another number. We can do this. Mathematically, this is perfectly valid. We can take that thing out the front. And what we've got now is 2 lots of 1 on 4 pi epsilon naught Q1, Q2 and R squared, which is basically just 2 lots of this thing up here. So if we double one of the charges, all we're going to do is double the size of the force. Seems to make a fair bit of sense. If you double the thing that's interacting with the force, or with the field, sorry, you're probably going to be, it makes sense that you're going to be doubling the force that that thing experiences. Now, I'm going to swap to, let's go, we'll go white for this one. What we're going to do now is change the distance apart. Just like with the gravitational force up here, if we change the r, the distance between the centers of the two masses, what we did was influence the size of that force. So if you make 2 planets go further apart, they're going to experience less gravitational pull on each other. The tide on Earth is highest when the moon is closest. The tide is lowest when it's furthest away from where we are right now. So clearly, when the masses are further apart, the force of attraction is a little bit less. Similarly with the electrostatic force, or Coulomb's law, if we have these charges a little bit further apart, the force of attraction or repulsion, should they be the same, is going to be a little bit less. So now with this one, what we're going to do is double the radius. Alright, I want you to remember this, try somehow, I don't really care how, but when we're doubling the radius, we're also, remember it's the radius squared, so we have to, if we're doubling the size of this thing, we have to square all of it, so we're squaring the doubling as well. So 1 on 4 pi epsilon naught, Q1, Q2 is our force. So if we were to expand out this thing down the bottom, so I'm just going to take a little snapshot of that, 2r squared, hopefully it's still in frame, 2r all squared is, you have to square the 2, 4 r squared. So now we've got this factor of, instead of that, we've got this. So we've still kept the 2 squared down the bottom line, which is now here. With fractions and all that sort of stuff, we can do the same thing as we did with this one here, except that 2 is on the top line, so it stayed on the top line. This 4 is on the bottom line, so it stays on the bottom line. So if a 4 is on the bottom line, what we're doing is multiplying it by a quarter. So if we double the distance, we've now got a quarter of the force. So think of it like magnets or static electricity. The closer you are, the bigger those attractive or repulsive forces are. When you're a little bit further apart, they become weaker a lot faster. So here, if we've got double the radius, we've actually got a quarter of the force. If we had triple the radius, we'd have a ninth of the force. If we had man, I should have done some easy ones of these, so I could change that. There we go. If we had 8 times the radius, we'd have a 64th of the force. Alright, so you can see as you're getting further apart, it rapidly changes the size of this overall force in comparison. Alright, now with Newton's third law, it pops up again and again and again and again and again. With Newton's third law, it talks about the force on one object being equal and opposite. Alright, so forces are vectors, remember, so we draw the arrows. The negative here just means it's going in the opposite direction. So we've got 2 forces that are perfectly equal in size, but they're completely opposite in direction. Now, if we look at the force on Q1, let's say we've got a positive charge here and a positive charge here. That's Q1, that's Q2, and they are r meters apart. The force on Q1 is going to be 1 on 4 pi epsilon naught Q1 Q2 on r squared. So now what we're going to have is a positive charge. These are the same charge, so they're same sign charge, so they're going to repel each other. So this is going to be a repulsive force that way. Alright, so from the perspective, I guess, of charge Q1, this guy here, it's got a force left. So if we were to look at the charge, the force on charge Q2, swap colours, F equals FQ2, 1 on 4 pi, the power editing won't save me here, Q2 times Q1 on r squared. This one here is going to be a force that way. Alright, so you'll notice that we haven't changed the size of Q1 and Q2. We haven't changed the distance between their centres. All we've done is changed which one we're sort of, focusing on, where we're looking for, what our, I guess, vantage point is. That's a horrible way to put it, but you can see that these 2 forces are just opposite directions. So Q2 times Q1 is clearly the same as Q1 times 2Q. R squared is the same, this ugly constant at the front is the same, so these have to be the same size, exactly the same size, but they're just going opposite directions, which means that thing is true, holds with Newton's third, which is really, really good. Now what we're going to do is add in a third charge, just for the hell of it. We have now got, let's go this one. We now have Q3, Q3, which is also a positive charge, but Q3, as you can see, is a bigger one. It's a bigger charge, and the distance between them is, I really should have done this better, is also r, just because. Alright, so if we have now three different charges, we can actually look at the perspective of different types of forces are acting on Q2. So we don't just have Q1 pushing it to the right. So if we ignore that, I understand that I can't block it out because I'm not on the other side of the screen. If we ignore this thing over here, we still have this charge getting pushed that way. But now if we look at just the pink and the blue one here, we've got a force that way. Now, if we're using vector addition, we say that, we magically come out that the force due to Q1 on Q2 is that way, and it's 10 newtons. Hopefully that's still in shot. It's 10 newtons, and we work out, because this one's, let's say, twice as big. This charge here is twice as big. Remember, if we're doubling the charge, we're doubling the force. So that would mean force from Q3 on Q2 would be double the charge, 20 newtons, miraculously that way. So now we can use vector addition to add those two things together. So if we have 10 newtons to the right, we have 20 newtons to the left, our overall force, so the force on Q2 is the force from Q1 on Q2 plus the force from Q3 on Q2. I should have called these A, B and C, it would have been way easier. So we can say that the net force is the addition of these two. It just so happens that this one is plus 10 and that one's minus 20, so remember to the right is positive, so plus 10 minus 20, and we've got minus 20 newtons, or 10 newtons, which is 10 newtons that way. Okay, so vector addition really handy in this case. The examples you'll see as we work our way through towards preparing you guys for the test and for the exam is that we don't just have straight line stuff like this, we also have triangles, but you can imagine what sort of triangles they'll be, and yep, so you'll have this sort of setup where you'll have a positive thing, a negative thing, and a whatever, some other charge, and there'll be lines of attractive force and repulsive force between their centres, and this is how you work out the size of those things, and this vector diagram will tell you the direction that it's ending up travelling in. Alright, yeah, that's all for today. Thanks.